Thanks, Tusang. Much appreciated. So I think we can jump into our first presentation. We have Dr. David Tinarwo. I will introduce him, and then just as a reminder, we'll take the questions after both presentations have been completed towards the end. So please go ahead, put your questions either in the Q&A or in the chat. Dr. Tinarwo holds a PhD in electrical engineering from the University of Kassel in Germany, and is a senior lecturer in the Department of Physics at the University of Venda. He's a seasoned researcher with a strong focus in renewable energy technologies, particularly biogas, wind, and solar energy. His current research places special emphasis on the bioenergy from animal, food, and plant waste, with broader goal of supporting sustainable rural development. He is also an active member of the SABIA board, contributing his technical expertise and academic insight to help shape the future of biogas in South Africa. Let's welcome Dr. David Tinarwo to the podium. Dr. David, over to you.
So thank you very much. Today I am going to try to do a marathon talk on the topic of biogas as a key player in South African energy transition. I put a lot of slides, but yeah, I am going to try and jump others and all the stuff and so on. But I hope I will manage to convey the message. So let me just start by saying we have challenges which we all know in the energy space, in climate change, and we are facing quite a lot of difficulties in the country, in the region, in the world, which are attributed to impacts on the climate caused by our sources of energy. And looking into the context of South Africa, we have passed through a very tough time where we had challenges in getting electricity always. So we had challenges of load shedding, we had challenges of down times where you hear this plant has got some problems, so we don't have electricity. On the other side, we had quite a lot of disasters, floods and other stuff and so on. And now the imperative is to say, definitely we need to move to better sources of energy, which are renewable energy. But there is a challenge then in this movement. The energy space, the electricity generation space where coal is mined and, plants are run, are operated, employs quite a lot of people. And these people then, when you think of changing to yet a new technology, one has to look at what effect, what impact will that give to those who were employed in those, companies, in those spaces and so on. So hence the need now to look at the transition, which is just moving from the old to the new, but without compromising, the welfare of people, the environment, and all the stuff. Unemployment is also a key issue, and it is scary to think of stopping something which is employing quite a lot of people and going to something which is employing less because of that challenge. So I will be looking at the biogas as a contributor to energy security and decarbonization. And I will also look at off-grid and rural energy applications and collaboration with the natural gas and renewable energy sectors in trying to justify why we say biogas can play a role in South Africa's energy transition. Okay, so I am going to present put my presentation through these points I've put there, looking at the context, which I have already summarized a bit, and also looking at the technology and the resource base, then looking at biogas and as an energy security, a strategy and a decarbonizing, strong partner. Then we also look at system integration and energy security, off-grid decentralization, which includes rural electrification and energy applications. Then a bit of some economics, finance, carbon, and lastly, I will try to, put in the gas sector in to see if biogas can actually be also, collaborating with the natural gas, which we are currently using. If time permits, or maybe it will be under, the discussions, the roadmap, policy actions, and of course, question and answers. All right, so as I have said, I talked about the already experienced, load shedding and supply gaps which we experienced. And we know the reasons. Some of them are, aging coal fleets, maintenance backlogs, grid congestion, and all the stuff. And we also talked about the need now to change from this old way of generating, generating electricity, but in a just way. So hence having an imperative of the just energy transition, which is actually guiding our activities as we move. Then in that we look at decarbonizing, but also we also look at whether this is generating the jobs which are needed, and also developing the industry, and as a result, developing the whole region. Then we look at what enables that. In this regard, then we push in to say biogas can actually be a candidate to solve these problems. Why? Because of the conditions which exist, these organic waste which we have all over, from agriculture and also from municipal activities, where we have quite a lot of organic waste which is thrown and causing actually problems to us. And if we convert them to energy and fertilizer in a circular economy approach, then that can really be helpful and fit in very well in the just energy transition. All right, just to give a bit of some concrete statistics of what the situation in the country was. We know during the time when we had quite big challenges. So I was presenting on the statistics of the situation which we experienced during the times we had challenges of electricity supply. Talking of energy availability factors, which were very low, and leading to persistent supply gaps and load shedding and all the stuff. So the table which is on the screen is just showing those information, that data. Then also on the other side, we look at the amount of waste which we generate from food and from our municipal sewages, from our agriculture in the form of poultry farming, and also abattoir, where we slaughter our animals for meat. We generate quite a lot of waste, which is really a problem in the country, to say how do we manage that. Then we look at now the potential of biogas then to solve that problem. So we say, why biogas then? Why do we think biogas can actually be a solver of these problems? The reason being that biogas technology, we can change all these organic residues to energy and fertilizer. And then that makes the core of a circular economy, where we will actually not have any thing which we would call waste, which goes unimproved to make a difference in our lives. So also then we look at what we get after having converted these to energy and fertilizer. In terms of energy, it has quite more advantages than the other renewable energy technologies. Take, for example, you have solar, you have got wind. And solar, you cannot say absolutely I can assure you that I will always have my energy, unless if you are saying I will, have a big storage in terms of battery, so that whenever we have bad weather, then we will still have electricity stored in the battery. But in the case of biogas, you generate biogas, whether it is raining, whether it is in the night, whether it is sunny, and so on. You can still produce biogas, put it in your tank, and start your generator at any time you want, and continuously run it like that. So you can dispatch the generator at any point, and can serve quite well as the baseload supplier. So also, when you look at the conversion of this biogas to energy, you can actually increase the efficiency of this by generating electricity, but at the same time recovering the heat for other uses. So that way, it suits very well as an efficient way of converting waste to energy, and serves quite conveniently more than these other technologies of renewable energy, which we know, like solar and wind. So what is this biogas? For those maybe who may be novices in this area, just a quick review on what this thing is. The biogas, of course, we get it from anaerobic digestion of organic material, and this results in a gas which is composed of many gases in it, which we call biogas. And the constituents of this biogas has plus or minus 60%. Of course, it ranges depending on the feedstock, and also the time maybe it has taken running. So we have as an average plus or minus 60% of that gas being methane. Then around 40%, plus or minus 40% of that gas being, carbon dioxide. Then these other three gases and others, which include hydrogen sulfide, water vapor, and nitrogen, they constitute less than 5%. So bulkily, we have methane and carbon dioxide. And the most important gas, which we are always, going for, is the methane, because the methane burns, and we need to burn it to get the energy which we need, convert it in different forms of energy, heat or electricity, and so on. Right. So to give you a rough idea of the equivalence of the biogas to other forms of energy which we already know. For example, 1 cubic meter of biogas is equivalent to about 6.1 kilowatt hour total energy, which includes electricity and heat. Then on electricity, because of the conversion then through the generator, which will lose some of the energy through heat, then we remain with about 2.1 kilowatt hour of electricity, or of electrical energy. So you see the efficiency there is that conversion from gas to electricity is around 35%. But of course, if you then harness the heat, then you improve the overall system efficiency. So the other equivalents are biogas with coal, with diesel, and with LPG. So you can see 1 cubic meter of biogas is equivalent to 0.4 kgs of liquid petroleum gas, the one which we buy from the garages and cook with. So this can actually really substitute that gas for cooking. All right. So how does it go? So just to quickly review how we generate the gas, of course, we have got organic waste, which is to be put in an anaerobic digester, which is a container, which is airtight and watertight. Of course, it does not leak water. It does not, allow unwanted oxygen in, so that the process can take place and then generate the gas, which we have already said. But one more important thing is, besides generating gas, the whole lot of the stuff which remains and which we call digestate, the remaining, slurry stuff, is a very good, a fertilizer for farming. And that means then that after getting your gas, you don't throw away what is remaining. You actually use it to replace the synthetic fertilizers, which are detrimental to the soil, detrimental to the environment, and even detrimental to the pocket. All right, so just a flow chart of what takes place in this technology. We look at how we move from the starting point until we get to the gas and use. So we have the first part is we have intake where we are receiving, of course, the feedstock, which is organic material, which can be in the form of animal waste or plant waste, and even municipal organic waste. So we, receive it, weigh it, separate, treat, pre-treat it, macerating it, cut it into into small pieces for easier digestion, then introduce it into the digester. The digesters can be of different kinds, continuous, steering, a tank reactor, or it can be plug flow, it can be dry, and also we mix it so that the process takes place very well. The bacteria, which is responsible for the generation of the biogas, can reach all particles of the feedstock. Then the gas comes out, then we can clean that gas and remove all those unwanted gases which we saw, like carbon dioxide, like hydrogen sulfide, and so on, and water vapor. We can clean that and make the gas almost, of high quality methane for either use in CHPs, combined heat and power generators, or in other generators, or in any other, function, or even to, run vehicles in that grade. Then also, as we have seen in the middle, after the biogas, we have got a part which goes down then to generating, a fertilizer. And this fertilizer, remember, it is a mixture of water and the organic stuff. And this water is a rich water, and we can actually irrigate using it, and while irrigating, getting fertilizer. So already I am pushing you to the understanding of how it covers all the functions of these other, forms of energy and, fertilizer, which we originally have. So biogas is covering all that. And if you look at from the sorting of the waste, carrying of the waste, to processing of the waste, and generating and making manufacturing of the generators to run, manufacturing of the vehicles to run on biogas, light equipment, and all the stuff. All those are already pointing to creation of jobs in the chain. So biogas is coming with a lot of job creation. If you look at farming, where you are getting the waste, quite a lot of activity takes place. If someone forgets about buying synthetic fertilizer, concentrates on getting fertilizer from the biodigester, so you can imagine how many people will be involved in that exercise. So this next slide here just shows a range of uses which I was talking about, like cooking, lighting, space heating, and even electricity generation. And on top of that, we can also store it in very big tanks, and already that points to that collaboration which I was talking about with the natural gas industry, and of course for running vehicles. Yes, we also need to just have a rough idea of the different types of digesters. Here in South Africa, we've got quite a number of types of digesters which are implemented. Some of them are brick built, which are done underground. Others are of course the floating dome, which is mostly found in countries like India. In South Africa, there are not very many this kind of digesters, but in India there are so many. But also here in South Africa, we have quite a number of prefabricated digesters, like for example the Biogas Pro, manufactured here locally. by a company which is a Gamma here in South Africa, and others which are coming. Many people are starting. Some are even using the Jojo tanks to make digesters. And also we have the tube digesters, which are easy to install, and they are also cheaper to buy and so on. So we have also the lagoon digesters, which are mostly suitable for dairy farming, where you want to capture the slurry lagoon from the milking parlor to actually capture it and put the conditions for biogas generation. So these are the different types of digesters which we have in the country. And of course, in our wastewater treatment plants, we have also digesters. And it's a surprise that not much has been really done to harness the gas. In most of these sites, you find they flare it, you see. So if it is not flared instead and captured and harnessed for energy use, then that will constitute a very good candidate to really fit in the just energy transition. Right. So I here summarize a bit. I don't know this now, since it is not in presentation mode, the slide might not be properly visible. Here I'm summarizing why biogas, why now, and how does it support the just energy transition. And we are putting the biogas in the middle. And now we have a triangle where the vertices of this triangle are talking to those components which it responds to, like the energy security and costs, where we are solving the persistent load shedding and high tariffs of the electricity which we are experiencing. So we can avert that problem from the utilization of biogas. And we are also actually decarbonizing the energy sector by using biogas, where we are, instead of leaving the animal waste to emit all the methane into the atmosphere, we make that methane emitted in controlled, situations and harnessed and used. And when we use it, when we burn it, we produce carbon dioxide and water. And when you produce carbon dioxide, if you look at the reduction which one has done from methane to carbon dioxide, is a big reduction. Then also, if we look at the creation of jobs, then there it really answers the proper linkage of the just energy transition, where we are saying we are having a lot of MSMEs, who are working in the different species contributing to the biogas technology. Others can be, manufacturing stoves, manufacturing refrigerators, heaters, and so on, which use biogas. And that is creation of employment and hence regional development. So the next part of my presentation then is just to, talk slightly about issues of what can be done. But otherwise, the main issue I have already, put it forward to say we have looked at the biogas as a means to, give energy. So security of energy. We have looked at biogas, looking at the social aspect to say the creation of employment and, creation of, organic food from organic fertilizer that improves the human health. So in that way, we are servicing an imperative from the just energy, policy. And also we look at, reduction of costs. We know currently our energy is so expensive, and by biogas, we can actually, reduce all those things. So now, again, when we look at its applicability, biogas, you can generate it anywhere where waste is, and hence suitable for decentralized electrification, decentralized energy supply. So we can actually hybridize, put in the hybrid system as a component of energy, where we are integrating, solar, biogas, wind, and others together. And we can actually say, if it is at a small scale, like, for example, what we are doing in Limpopo, where we are working in small-scale biogas digesters, we look at a school. A school needs electricity for its, functions in offices, in classes, but also needs heat for its cooking. What do we normally see? We see piles and piles of firewood where they are burning firewood for cooking. So if you integrate biogas in that space, what is going to happen is the cooking can be easily taken, care of by biogas, while you can integrate other forms of renewable energy like solar, which will be taking care of the electrical part. Why do we prefer it that way in those systems which are small? Because, of course, running a generator with a small system may not be very economical for a biogas system. You need to be slightly bigger so that you can run the generator for a reasonable time. All right. So also we have some functions in agro-processing, microgrids, where we have a biogas playing a role in a dairy, cooling and abattoir, dryers, and so on. And we also have recovery of heat, and we can even improve, as I have said, this biogas to reach qualities of our natural gas. So that is a possibility. So that way already we are saying we can actually make biogas collaborate with the natural gas. On irrigation, agriculture, as I have said, we have challenges of water in the country. We use water for generating biogas, but at the same time, that water is not used and lost. It is still recovered and utilized for irrigation, and which is irrigation not just with water, but with water which is improved with the minerals or nutrients for the plants. So hence we call it fertigation, where you are fertilizing and at the same time, irrigating. So we also have social infrastructure, as I have talked about in the schools. We are, putting, a biogas digesters to actually, one, manage waste. Imagine is a school which is doing agriculture, which is doing piggery, which is doing chicken, poultry, and all the stuff. The school will be very smelly. And now the biogas technology comes in to make the environment livable, and also to improve the energy, quality of cooking in that school, and the healthy in terms of organic, crops which are good from the organic fertilizer. So yes, of course, we have so many strategies of how that is employed, and the involvement of local SMEs and so on also is a contribution to job creation and solving the challenges which the country faces of unemployment. Right, this is talking again to those MSMEs and cooperative models where they are working together with those institutions like schools and hospitals and all the stuff. Then also, of course, in doing that, we need also to look at compliance in terms of safety, how to use it, and so on. Although we can safely say at lower pressures, it is even much safer than the LPG. But of course, details of what needs to be done in order to secure safety of people in the use need to be outlined wherever it is being used. Right, and monitoring, of course, this is when you are having the systems which are working. We can also do some, improved monitoring systems of this to see how our systems are working even remotely and so on. So you can see all those are talking to need for creation of employment, research, and so on. So many youths will be involved even to design those SCADA monitoring systems. They need to be designed by people and hence actually creating employment for them. Then, of course, I was talking about this collaboration with natural gas and why do we need that? Of course, because the biomethane can actually be improved and can be also used in hybrid systems where you have got other forms of energy. And also gas supply needs to be, properly controlled and all the stuff. So as I have indicated, I think this slide I've once shown it, so which is coming back to consolidate the collaboration which is possible between the natural gas and biogas. So we know of these containers as for natural gas, but yes, we can also containerize for biogas. However, I need to mention to say, yes, while we can clean the gas, containerize it, and even put it in those cylinders, but it won't be economical viable if we are talking of small scale biogas systems. This is only reasonable or viable economically when you are looking at larger systems. I think let me just stop here and allow questions to come. I have so many slides, but I think the gist of the story, which is looking at the biogas in the just energy transition, its contribution, its role, I have touched. So I can stop here to allow questions so that we can even explore more during the question and answer. Thank you very much.
Thank you, Dr. David. So as I mentioned previously, what we'll do is we'll take questions at the end. So instead, we'll go to our next presenter. Thanks again for the presentation, Dr. David. I will then introduce our next speaker, and that is Moses Motaung. Moses is a director at re-energise Africa, a company that provides specialized operations and maintenance services in the biogas industry. Re-energise Africa expertise span from end-to-end project conceptualization, ensuring waste to energy projects are both technically sound and profitable, to the supply of critical spare parts, gas cleaning systems, activated carbon solutions, and locally built filters. The company also provides oxygen and nitrogen generators, strengthening the reliability and efficiency of biogas operations. With his leadership role at re-energise Africa, Moses brings a wealth of practical insight into both the technical and operational dimensions of biogas project development and management. Today, he will share his perspective on innovation in biogas technology and how these advancements are shaping the industry's future. Let's welcome Moses. And Moses, you may go ahead and share your presentation.
Thank you, ladies and gentlemen. Thanks to the Prof as well for a very insightful presentation. So today I'll actually, as compared to the previous time I had a presentation, today I would like to go into the equipment that is used in the gas production. So basically, this is more like a closer look, at the digester and the different parts of the digester, how they look, what they do, how do you operate them, how do you maintain them. So it's a long presentation, but I would like just to go through quickly, give you a feel if you are a person there who wants to or who would like to have a digester or who would like to operate or maintain a digester. get to, because I mean, most of the time what people sees on the drawings is more, it's the tank, and then that's all you see with its green top. You don't know what's happening there. So that's what I would like to go into. It's not more about the process, but it's about the equipment itself, what we have there, and how it looks like, and so forth. So it's going to be a lot of pictures that shows you different things. This is just one part or just one type of a digester. So I'm handling here the continuously stirred tank, which is used mainly in Germany. I think I haven't seen anything except, or maybe the difference was the digesters that I saw at the waste treatment plants are different. They're like a big spherical digesters, but mostly the farm digesters, which handles silage, maize, and all the cash crops. They are all continuously stirred tank. Okay, but let's jump on to the presentation. So one of the most important things to recognize is that digesters are actually generating an explosive gas. So if you are working on a biogas plant, you need to be aware of this, and then you need to be properly trained on this, and then you need to know as an operator or even a maintenance personnel who works at the plant, know your zones, which are EX zones. This, I think, is an European labeling for explosive environment, and also explosive or equipment that is used or that is manufactured to operate in an explosive area. It will have the two the signs that you see here, or the labels that you see here with EX. So EX, or this is the ATEX standard. They call them ATEX standards. So there is ATEX standards for gases and also for powders. But in this case, we are looking at the gases. So there is zones. For gas, zone 0, it means that there is danger. The danger of gas is present. It's present permanently. Like in this case, if you look at what we have here, this is basically a roof of a digester, and then this is the tank. You see, this is a post digester, and this is the digester. So this is the roof. So in the plans, you would see the plans of a biogas plant will have plans like this, or areas that have been identified, and that means in those areas that are identified as having gas, equipment that must be used there must be EX or ATEX rated equipment. In South Africa, we use, I think, intrinsically safe equipment and explosion-proof equipment. So that might be, viewed as an equivalent when we're trying to address issues where you don't need an ignition source or a heat source or a spark that can create an explosion, because the gas is flammable. So it's important that this you don't just bring anybody. If it's a millwright, that millwright needs to understand something about the health and safety and the fire, and specifically the fire issues at the plant. So that's very important. The same applies to the operators, that they understand this, because fire can occur. But not only fire, this gas is also hazardous if you inhale it. There's issues related with that. So I think in the future, we'll deal maybe with a presentation that handles health and safety in totality regarding biogas operation. So it's one of the big topics that in Germany, I know there is institutions that actually offer safety training on handling of biogas. So it's something that you need to have. All right. So I'll step off from there now. So now we'll look at the tanks, the biogas tanks, basically the roof, what what does the roof looks like, heating, agitation, and then auxiliary equipment. The tank roof of the biogas digester, let me just go back if I can. Okay. So if you look at, this is the type of digesters that I'm talking about. These are the stirred, continuously stirred tanks. So the roof is really this dome shape membrane. So that's what I'm going to be talking about now. So this is called a floating tarpaulin with double membrane. So it's a tarpaulin, which is basically a canvas. It has a double membrane. So it has an outer and inner membrane. The outer membrane is PVC membrane. It's coated with anti-UV protection. So it's basically a cover that protects the inner cover. I'll explain. So that's the top cover, the outer cover. The inner cover is it's a low density polyethylene membrane. This one is for gas storage. So the top cover protects the bottom cover because UV damages plastics and rubbers. So you need that. So the protection that the outer membrane offers is for against the sun, but also against moisture like rain, and then also the forces that can be imposed on the gas storage membrane by wind and rain. So the outer membrane protects against that, while the inner membrane is used for gas storage. So basically, as the gas gets generated, the inner membrane expands to provide a gas temporary gas storage in there before it can fit it to another tank, which is a storage tank. There is a sealing tape and a clamping pipe. You'll see this, the slides on this mounting rail, and there will be a fan. So a fan is very important. I think I need to mention what it does here, but you'll see on the next slide. What the fan does, it actually because it blows air between the two membranes, the top and the bottom membrane. So if the membranes are not, they are not blown, there's no air in, the top membrane will actually collapse. So you won't see dome that you're seeing. If it collapses, it will be actually level, flat, meaning that if rain comes, the weight of the water will actually will actually create pressure on the thing, on the digester. The digester has a very low pressure. It's in millibars, around 30 millibars in there. That's the pressure you have. So if you have a rain, on top of the membrane, it will actually create problems with the gas that's being generated. So the top membrane, so when you blow the air in between, it creates a dome, meaning that now when the rain falls, it will just slide and then go to the ground instead of sitting on top of the roof of the digester, and then the wind as well will be diverted or deflected. It won't be applying a lot of force on the inner membrane, which is a gas storage. There is a ventilation flap for pressure control as well between the outer membrane and the inner membrane. There is a safety valve that helps for overpressure and also under pressure. And then there's also a gas level indicator on the tank. So we're looking at the outside, like I said, this is the flap. And then you can see now, this is a more close-up shot. You can see the top membrane, which is green, the black one, which is now the gas storage inside, which is trapping the gas storage. And then this is it's a pipe or hose that is pressurized to clamp, which clamps the two membranes together to create a seal. I think if you can see on here. You do see my cursor, right?
Yes, we can see it.
You can see it.
Yeah.
Okay. So where I'm moving my cursor, that's where this hose is. It's compressurized. It's pressurized to create a clamp on the tank to seal the two membranes together. So you can see again, though I'm not talking about this today, but I'll just mention, you can see there is a net here. Inside there is a net before the inner membrane. So the net, most of the time, what it's used for, it's used for biological desulfurization inside the digester. So it will be coated with a slurry, and then there is an oxygen generator that will blow in a tiny bit of oxygen to enable a reaction to happen on this net. So I've had the opportunity of being traveling with the maintenance guys, or the guys who overhauls and change the equipment for the digesters. Once, I don't know, after 5 or 10 years, the digester gets emptied, and then they take out stuff. So you can see on the nets and then on the roof of the digester inside, you would see the yellow sulfur collecting there. But I've just learned that this net also, with time, there becomes a lot of buildup of elemental sulfur, which is it will actually cave in and then fall into the digester, and then it will go out with the substrate, with the digestate, and then the sulfur gets added back to the digestate, that can, which is used as fertilizer, as the professor have already indicated. So that's part of what this does for the. And then you can see the pipe that I was talking about, that is pressurized. So there is a compressor as one of the equipments that is used in this case. On this slide, on this presentation, it's basically a number of tanks. It's not just one tank. There is storage tank, there is secondary tanks, and also storage tanks for gas. So the compressor supplies pressure to compressed air to a number of tanks. Hence, you have a manifold with distributions for different areas. So here are just the daily checks, which are, mundane, nothing special. You have to make sure that the compressor is operating, because compressed air is used for different things. If it's not, the compressor is not working, you will have a number of instrumentation and other things not functioning properly. Making sure that there's no leaks. Compressor can operate while it's still leaking, has leaks, but it will actually waste a lot of energy, because it will be part of the operation would be saving the leaks instead of the purpose that it was designed for. Just make sure that things are tight. And then I think here, this is a better picture that shows that clamping pipe that I talked about, that you can see. This is the top of the tank, the roof, and then this is just a bit of the membrane, so you can see where it goes, and it gets supplied by a compressed air. This is still the compressor. It's just basically things that you need to look at: the condensate, oil levels, and ensure that the valves are open to supply areas that are required, and also the chiller or the cooler for the compressed air cooler, to ensure that condensate is removed from the compressed air. Okay, this is more of the same. It's just a distributor for compressed air to different areas, digesters or storage tanks, and then also to the instruments that uses compressed air. Okay, same picture. Okay, so now we come to the fan. We've spoken about the compressor, what it does. Now the fan, I had mentioned earlier that you have the fan blows air between the inner membrane and the outer membrane. So this is the picture that you see here of the fan. So your fan is here, it's a small fan, the inlet, and then the motor is somewhere here. And that would be an ATEX rated motor. So like I said, ATEX as well, what I forgot to mention is that in order to work on the ATEX equipment, you need to be appropriately certified. And then the company, if you take it for overhaul for whatever, the company that does this needs also to be ATEX certified or approved, because there needs to be tests that needs to be undertaken to ensure that this motor cannot be a source of ignition for gas. So it's very, very important. These are the things that we don't look at closely, but these are the requirements for a successful operation of a biogas plant. So it says the fan offers stability for the membrane. It offers pressure to help the gas to flow through to the vats. Vats in this case, other storage tanks. And it works continuously. And then if there is an issue with the fan, it has to be attended immediately, because that can have a catastrophic effect on the whole operation. So it's a very important piece. It's a small piece, but very, very important piece. So these are just the views of the fan. You can see the grills. So this grills needs to be obviously inspected and cleaned to ensure that the air passages are operating properly. And then also then, with maintenance, if we have maintenance people here, you also use your 5 senses to identify if there's issues. You can listen to vibrations, heat. If you hear abnormal noises, obviously you need to, as an operator, you need to call maintenance to come and check, because this item needs to be operating continuously. We spoke about the ventilation flap. So it's a flap on top of the roof. So it's the one that it basically regulates the pressure between the outer membrane and the inner membrane to allow that the digester has a safe working pressure, but also the gas can actually be evacuated from the digester to the storage tanks. I'm not going to go into the settings because these are settings, but it's not really necessary. But my focus here is understand the bits and pieces of equipment that you find, which actually informs the maintenance and also operations activities that need to take place at the biogas plant. And there is also slides, which I'm not going to show you here. It's automation slides, because most of the instrumentations are monitored in the control room on the SCADA system, and then also there is activities, automatic activities that takes place if the operating parameters are not in line or are out of the limits that has been set. But that's not the focus today. The focus is actually instrument mostly the mechanical equipment. Let me say, to be specific. So there's also a safety valve here. Safety valve, it also monitors the overpressure and under pressure. And then there is limits. You can see, like I indicated, that the digester operates in the millibars. So under pressure between 0.5 and 1 millibar. And then it also opens at overpressure of 3.5 millibars. So it also regulates the internal. Now it's the internal pressure in the digester, not the flap is the pressure between the inner membrane and the outer membrane. These are just more the details of how this thing operates. It's a two operation thing. The top part looks at the overpressure, and the bottom part is under pressure. And this is just a schematic. So there is also a need to understand how high or the level of substrate or substrate in in the digester. So there is a level gauge that is calibrated for, levels for 20%, 60%, and 100%. So this help works together with the feeding of digestate of the substrate into the digester. So the levels need to be known, and gas yields and so forth. All this goes into the SCADA to perform also automatic functions. Mainly will be the shutdowns or prevention of certain activities to ensure that the digester is operating safely. This is just a schematic. I just kept just one of this to show you what the screen looks like. In this case, they have 3 tanks. One is a secondary tank. The other one would be probably a storage tank. And all the parameters from instrumentation will actually be will be monitored in the control room by the operators. And then the settings of different equipment, for the valves and so forth, or for the instruments, will be done on the screens inside in the control room. So going further, one of the most critical things in a biogas digester is actually to maintain the temperature of or the temperature that the microorganisms in the digester loves or are able to function properly. So in this case, it's a mesophilic process. Temperature is around 40 degrees, and then what you're seeing here is actually a digester that's open. You can see at the top, there's nothing here. There's a center post, and then there's those beams that balances the net that I've shown you, and then also during installation, it also balances the inner membrane. That's what you see here, and then the heating is done through this. These are pipes, plastic pipes that goes around the digester. So this is what heats up the substrate. So these pipes are the pipes that are used to move water inside the digester for heating, for keeping up the required process conditions. So this is a very important aspect of biogas digestion. If you don't have the temperature at the right temperature, there will be no gas produced in your digester. So it's very important that you're aware of that. So this is just a bank of pipes going to different digesters. So I'm not gonna talk more about them, but I think what's important here is that the inlet temperature should be around 70 degrees to allow for the dense mass of the substrates, and then also the losses as you transport the water from normally most of the time you will find that in Germany mostly the hot water will be coming from a CHP, because I'm sure 90% of the plants there, they upgrade the gas from biogas to biomethane, but some of the gas is actually used in a CHP to generate electricity for the farm, and I think they also feed it into the grid. And then so on the CHP, they will actually recover the heat from the exhaust, and also from the body of the engine, from the lubrication. That energy that's recovered then becomes the energy. It gets dumped into water to then heat up the digester. Okay, this is just the labeling. This is basically automatic vents for releasing air out of the pipes. So this is necessary when you have when you are transporting water, and mainly hot water, to release air, which can cause flow fluctuations and also vibration in the pipes. So the next other important piece of equipment in the digester, so it's not very clear here, but if you look at my cursor, so there's a post here. I think there's a post here. You can see the white post, and then there's another one at the back, or this one. So on this post, you would see the agitator. It looks like a boat propeller. So it has the blades, and then it turns. So the functions of it is to maintain a homogeneous digestate inside, so that all the digestate that has been fed is accessible to the microorganisms for digestion and or for fermentation for the creation of gas. But it also helps, or they help with to avoid floating layers. I'll show you the pictures. Sedimentation of heavy substrates and gas pockets with thick digestate, and also other biological problems that can arise from digesting a digestate that's not homogeneous, or the substrate that's not homogeneous. So this is a close up. You can see here is the blade. This is one of the agitators. I must say, having worked with this thing, it's one of the most difficult ones to remove and put in again. It's quite. It looks easy, but it's quite challenging. So you can see one here, and then there's another one here. It's on a rope, meaning that its position vertically can be adjusted, but also there's a cantilever here, beam that goes towards the inside of the digester. So this also allows for a horizontal movement or adjustment of this piece of equipment to access maybe towards the center, to avoid like a dead zone. So you can actually move your stirrers or agitators to different places. Here it's operation of the agitator, but this is basically the mechanism. You can see it has a winding thing, and then it's like a sheave or a pulley with that rope that you saw on there. So you can actually wind, meaning putting this thing up or unwinding back under gravity, it can then go down. So you have from the outside, because remember, once you have closed the digester and then it's you have actually fed in the material, you can't open anymore. So this is now the mechanisms that you can have a bit of control of the equipment that's inside. And then you also have this lever that can be pulled forward or backward to move, to horizontally move the position of the agitators. So let me just see what the note says here. So this needs to be completely covered with digestate. You don't want splashing and creating a whole lot of splashes inside. But their operation needs also to be observed to make sure that they are functioning properly, because you need them. Things like unusual noise, vibration, and then also creasing of the actuators or the adjusters for it needs to be done regularly. And I think the other thing that's more important as well is to ensure that the rotation it's not counter. They are all rotating in the same direction, to ensure that you have a nice swell of the digestate inside the tank. So this is the pictures that shows you if the agitators are not working right. You can see now how it looks in here. This is not what you'd like to see. You'd like to see uniform, liquidy, moisture substrates inside the digester, and you can see now where things actually fell apart completely. Now this is, I mean, this is at the top of the digester. I think this digester went bad because you can see that's the dry stuff right at the top. So probably level probes and other things that tells you about the height didn't function for whatever reason, because you can't have the digestate or the substrate being this high in the tank. Other things that we talked about, this is a double rod probe. This is basically, it's there is initially I have in the earlier slide I had showed that there is level indicators for the substrates inside the tank, but I think there was a warning on the slide that those are also approximate. It's approximate. It's not definite that where the level probes tells you that the substrate is. So there is an ultimate stop or ultimate detector, which is this one, that if you didn't read properly or there was an issue with the level indicators, this will actually tell you now that there is material that's hitting the probes, and then what will happen is that it will disable further feeding of the digester to ensure that the previous situation that we've just looked at, or where the substrate is high in the tank, happens. So these are those safety controls. There's also pressure sensors for the inside, which if the pressure valve is not working properly, then there will be this catch, which will then ensure that appropriate action takes place if to see what's happening with the safety valve. Lighting. So because now we are in this area, it's actually now towards the inside of the digester where it's zone 0 according to our ATEX rating, meaning that gas is there permanently. So you have lighting there to see, but this lighting must be ATEX certified. So it comes again to the point of where the zoning around the digester, and then the type of the equipment that must be there. In fact, even all these instruments here, they are ATEX approved or ATEX certified. They cannot create high enough current to create sparks, and then the enclosures are also sealed completely such that no gas can actually go in there. And then the heat generated by the item itself, but it's not sufficient to create fire. So that's very important to note that. Now this is now further away from the tank itself. Now we have the feed hopper and a premix. So the hopper stores the substrates that comes in. Like I said, in Germany, in this case, most of them are cash crops, so they will have maybe co-digestions of different cash crops together because maybe the yields are better, or the digestion takes place better if you have multiple crops being co-digested together. Then the premix, this one mix the substrate together with digestate before it can be fed, or before it can go into the cutting. There's a rotor cut. There's like a pump that slices digestate into smaller, not digestate, substrate into smaller pieces to make sure that the nutrients are available or accessible to the microorganisms. So the idea here is basically to achieve a homogeneous mixture in the digester. So you don't want the microorganism to struggle. You want them to find the substrate in the form that they can actually work on it directly and produce more gas, because the name of the game here is gas production, not struggling. So these are the parts of the hopper. The hopper has a sliding floor. You'll see what a sliding floor does. It has weights. So there's also the load cells, that because it's high up, and then it's fed by machinery. So you need to the system needs to be able to indicate what level or what tonnage is in there, but also for process control, the tonnages are important. There's also a horizontal screw and a drain screw, riddling screw, and a shear screw. So these are the components of the hopper, and it's important just to know about them, because they are maintenance significant items, which in the future, when the system, or even if not in the future, because of the corrosive nature of the digestate and the digestate and the substrate that gets mixed, you might find that this equipment breaks, and there is ways to actually look after it to ensure that it's operating reliably. The premix has a feed pump, rotor cut. So feed pump is a feed pump from the for the digestate that gets mixed with the substrate. The rotor cut is now for cutting the mixed stuff together to make it homogeneous for the digester. And then there's the evacuation pump, and then the DRS. This is the parts that remove debris from our feed. So you would like the feed to be free from metals, free from rags, free from things that do not have a business being in a digester. So you'll see there's some pictures. So that's your sliding floor, which is operated by hydraulics. This is actually the hopper. So it has a moving floor that pushes the substrate forward towards you'll see at the end there is a screw, and there's a screw at the bottom, and then there's something that looks like a plow, which actually cuts. It does the pre-cutting of the digestate to ensure that when it goes to a rotor cut for a fine cutting, it's already sized. So this is part of the sliding floor of the hopper. And then circled in red here, these are the load cells that gives an indication of the tonnage or the load inside the hopper. And then this is a close up of the load cell. And then you have the screws. There's the screw, and then there is okay, number one is the dangling screw. This is this one. It's got blades on it. And then number two is the shear screw, and number three is the transfer screw. So this works together to size up the substrate for the next station. So this is just a section of the screw parts that will need attention during operation because of the aggressive nature of the juices that come from the substrate. And this is just safeties for the hopper. These are the emergency stop button. If somebody sees something that's not operating effectively, this can be pressed to stop the operation, because the hopper is not stationary. It's stationary, but it has a moving parts, the floor, and then the screws that I've shown you now. Sorry, I had that. I still have some time, Chair.
Actually, how many minutes do you need to complete?
Maybe
so 8
2
minutes
or 3 minutes.
Session. Okay,
Yeah.
please go ahead, and then we'll leave the remaining that to address questions.
All right, that's fine. Thanks. So this is hopper security. So the door of the hopper as well, it's also a magnetic lock as well, or it detects whether the door is open or not. If the door is, because there's rotating things inside, so it won't allow, if this thing is not made, it won't allow those items, those pieces of equipment to operate, just for the safety of these things. And then there's also the twin rod probe. We've already seen it in the digester. You also have it here as well to measure the level inside this thing. It's another additional security in case the load cells are not working properly. Then when this thing gets hit by a load inside, then it will actually stop feeding and other things. So then it can be attended. So there is a lot of built-in securities. Like I said, this is one of those plants that's highly automated. There's a lot of sensors everywhere to ensure that things are operating optimally, but also safely. Premix feed pump. This is just the picture of the pump itself. It's an interesting pump, though. It's not a centrifugal pump. I forgot now what the name is called. What it's called. It's pushes, because you're dealing now here with not so flowing stuff. The digestives is still not the digestate. The substrate is still solids. Hence, it gets mixed with the digestate to make it flow a bit. But yeah, it's not a centrifugal pump. It's a different pump. The rotor cut, this is the one. So what it does, it mixes the digestate and the substrate. It grinds the mixture, to the levels that are required. And then at the same time, it has a knife inside, which actually the system tells you the condition of the knife, and then if it reaches, the warning is at 20%, and if it reaches 1%, it can be changed. Sorry, I was just plugging in my computer while I'm talking. So this is the rotating mechanisms with the knives that cuts or in fact, there is the knife head that has been taken out. So it measures it measures its condition. And then pre-tension system. So these are the operating equipment that helps the rotor cut operate effectively. It uses compressed air. So these are just the parameters of the compressed air in terms of pressure required to make this operate effectively. So there's an alarm, the settings 7 to 10 bar, and then alarm 3.5. And then pre-stressing of the pressure on the knife is 4.8 bar. So these are just the things that gives you proper operation of the rotor cut. Locking chamber, and then there's a premix pump. Yeah, so these are just the components of this equipment. We're not going to go into this at this stage, but it's just to show you different pictures of what we have. Yeah, I think I will stop it here, Chair and the team. I think I hope I have shared a bit of intimate close-up of the complexity or the kind of equipment that's at the digester, so that you have a bit more appreciation of what really goes down beyond just the biological process of generating gas, but the actual equipment that helps you to generate this gas effectively and also safely. Thank you.
Thank you, Moses, for the presentation.